Alrighty guys, welcome to tutorial number 33, and in this tutorial I want to talk to you guys about Kepler's second law. So in Kepler's second law, he pretty much is saying that a line joining a planet and the sun sweeps out equal areas during equal intervals of time. Easy enough? Okay, ready to move on to the next video now. I'm just kidding. I know that whenever you read this law in a textbook or on the internet, it's really hard to visualize. So let me go ahead and try to make an example that is a lot easier to understand. So we already know from Kepler's first law that planets orbit the sun in an ellipse. Now ellipse is basically like a potato shape, and let me go ahead and draw the sun at one of these points. So the sun, let me actually make it yellow because you know the sun. Okay, right here. So here is the sun right here. It's a pretty good, actually I can't even lie. That sun looks terrible, but you know, it gets the point across. So during 1 year, we'll say it's the Earth, the planet Earth makes one revolution around the sun in this direction. So it is at all of these points on the white line during a year. However, it's at different points. So we'll say in January it goes from point A to point B, and we'll say that this is a 30-day time frame. Now maybe during May, this Earth would be over here. So this is C, and this would be D. Still 30 days, but at a different location. So why is this important, and why do we care where the Earth is in relation to the sun? Well, it's because Kepler said this: if you were to put a point directly in the middle of the sun, and you were to connect a line from C to the point, and also D to the point, and you calculated the area of this right here, it would be exactly equal to B to the point and A to the point. And I know, wow, I was way off on that one. Let's see if I can draw a straight line. And no. But anyways, not important. So this thing that looks like a pizza is, they say pizza? Pizza is actually area that Kepler said was exactly equal during any period of time. So even though the distance from A to B is different than C to D, now aside from the distance, the speed of Earth between C and D, in A and B, it's going at different speeds. During these 30-day time periods, this one in January and this one in May, or whatever I said, the area, this blue area, will always be the exact same. So basically, even though that this pi, AB pi and CD pi, may be a different shape, the amount of pi is always going to be the exact same. Pretty sweet, huh? So then Newton came along, and of course Newton always had something to say about something. He wanted to explain how Earth could orbit in this particular way. So, okay, messing up already. So here is our path of the Earth, and let me go ahead and draw my sun again. Since, you know, I'm pretty good at drawing suns, not to brag, but, I mean, I've never seen anyone draw a sun that good. So now we have our Earth right here, and I might as well put a big blue E in it, so you guys know that this is the Earth. Now, a lot of people were wondering, alright, first of all, why didn't the Earth get sucked into the sun if the pull of gravity is always pulling on the Earth? And why is this able to orbit in, you know, not a perfect circle? Because it might make more sense if the Earth orbited in a perfect circle with relation to the sun. Well, Newton said that, you know what? There isn't only one force acting on the sun. There isn't only gravity, but the Earth, since it's moving, and everything that's moving with mass also has another force acting on it, inertia. Now, inertia, remember, pretty much says that things are going to keep moving in the direction that they came. So gravity is pulling it towards the sun, and inertia is pulling it in the direction that it came. So it came from here in this direction. Inertia wants to keep pushing it or pulling it in that direction. So whenever you add these two forces of gravity and inertia, that's what causes it to pretty much average out and move in this direction right here. Now, no matter where the Earth is in relation to the sun, whenever these two forces are combined, whenever you take the average of that, that's how you get this kind of elliptical shape right here, which whenever you add the force of gravity and the force of inertia, it calculated to perfectly make this elliptical shape. So that is how Newton basically verified Kepler's second law. So just remember, Kepler said that in his very first law that the pieces of the pie are always going to be the same size or have the same amount of area in a given time frame. And Newton says that when gravity and inertia, these two forces that are acting on the Earth, are combined, it's going to cause this elliptical shape around the sun, verifying what Kepler said in his first two laws.